Hello everyone, we are excited to share our final project for ORB-530. Our team consists of Cao Tianyi, Chen Jiashen, Jin Zonggao, and myself. Over the past few months, we have been working to enhance the performance of both front-end and back-end of ORB-SLAM3 and VINS-Fusion, two of the most widely used SLAM systems. First, I will provide an overview of what we have accomplished. This project aims to boost the efficiency and effectiveness of ORB-SLAM3 and VINS-Fusion, which are critical to the SLAM community. Our work involves significant research and modifications, which we believe will contribute meaningfully to the field. Throughout this presentation, my teammate and I will outline our method and the result. Please note that some modifications are preliminary and based on our current understanding. Now let's delve into my contribution. The front-end modification of the ORB-SLAM. ORB stands for Oriented Fast Key Point and Brief Descriptor. It uses feature point to implement the visual odometry. A key aspect of our enhancement involving ensured the system could extract a substantial number of high-quality feature points. These slides show that the general process of how ORB-SLAM extracts oriented fast key point. Initially, the fast algorithm assesses the brightness of the pixel on the surrounding circle for each pixel in the frame. A pixel is designated as a key point if at least 12 out of 16 surrounding pixels show intensity either above or below the threshold compared to the center pixel. After detection, various operations are performed to maintain scale and rotation invariance. After that, non-maximum suppression and other techniques are also implemented to prevent the cluster of the key points. However, this process can indefinitely reduce meaningful edges and key points in certain scenarios. To address this, we implement bilateral filtering and the Sobia operator to pre-process the image frames. The bilateral filter smooths the edge when preserving edges, mitigating the effect of noise and minor color variance. The Sobia operator then uses the refined image to detect and highlight significant edge, essential for the future localization and mapping text in substantial stage of the ORB-SLAM. This enhancement ensures that input to the feature detection algorithm is optimized for the both accuracy and performance.
So, as a matter of fact, the original ORB-SLAM3 chooses to use the G2O as the method to do the optimization for the backend, playing a role in minimizing the errors generated from the front end and the other part. The way to achieve this goal is to set the keyframes as the vertices and set the corresponding mapping points as edges, and then constructing the bounding relationship between the vertices and edges. Then it will send them into the G2O optimizers. But we just found out another choice, which is called the GT-SAM, which is also applied in our last homework. Uses the factor graphs constructed by the variables. For here, it will be the keyframes, and the factors. For here, it will be the mapping points, and uses the linear optimizations to solve these factor graphs to find out the optimal choices. Both of these methods share some similar features, such as they both use the LM as their optimization techniques, but they work in different methods to process the errors. So we chose to add the GT-SAM to further deal with the data which has already been processed by G2O to hope to improve the performance of ORB-SLAM3. This is actually the result path gained after applying our method. So it's clear to see that after we apply the GT-SAM after G2O in bundle adjustment, the result is closer to the ground truth and generates fewer errors in the magnitude.
Hi, this is Jeffrey talking about the front end of VINS-Fusion. So for the first half of the project, we spent lots of time trying to figure out the fusion's mechanism of the VIO part of a typical VINS-Fusion system. It turns out that the VINS utilize Shi-Tomasi algorithm for feature points detection. It essentially calculates the gradient covariance matrix M with respect to the rate of the intensity change. And the score R will be then calculated, which is identical to the smaller eigenvalue of the covariance matrix M. It is used to rank the feature points based on their quality. And after this step, VINS uses Lucas-Canade optical flow to match feature points between different frames. It basically uses the rate of change of the intensity of a certain pixel within a window to calculate the velocity of it. And I think the equation from the intensity of a pixel, given a W times W size window, we have a total number of W squared equations to solve, leading this problem to Z squared optimization. And after this step, the EuRoC optical flow algorithm basically keeps matching pixels between the left and the right cameras and starts from the coarse to the fine just to ensure that the result will converge. And similar to ORB-SLAM, we also implemented a bilateral filter as well as a solo operator before the image to factory estimator. This will enhance the corner features theoretically and reduce the noise.
For the backend part of VINS-Fusion, at first we try to integrate the basic framework with the dataset method in the homework 5, but as the VINS-Fusion using the sliding window postgraph method through Ceres, the logic is kind of different with the dataset we used in homework. We didn't successfully merge them well. So in this project, we just analyzed the adjacent edge and loop edge performance in the postgraph optimization. Now here are the two tables on the EuRoC MH1 and 5 datasets. You can see we try to change the adjacent edge number from 5 to 2 or 8, and also we remove the loop edge to explore its performance. And we find that in both datasets, as we remove the loop edge, the position accuracy decrease. And interestingly, in MH5, as we add more adjacent edge from 5 to 8, the rotation accuracy increased a lot. So in the final test, we decide to keep the loop edge and try to add more edge and more adjacent edge to get a better performance. But actually, it could improve the accuracy, but it's not a robust and good way to optimize it. And here are the results of ORB-SLAM3 and VINS-Fusion on the EuRoC MH5 dataset. Each graph had 5 trajectories, including the ground truth data, original data, front-end and back-end modification data, and finally the combination of the two modifications. And in conclusion, we find that in ORB-SLAM3, the IMU plays a significant role when we use the stereo camera and IMU together in the system. And if we only use stereo camera but without IMU, we can get reasonable improvement based on our modification. But as we try to combine the front and back-end modification together, the improvement will be reduced. And in VINS-Fusion, our modification not quite effective and get a robust performance. And the bilateral filter and solo operator will increase the noise, which result in a failure localization in MH1 datasets experiment. But this modification will not influence the IMU, and the IMU will always help to generate a reliable pulse.